Hi everyone, gonna start ENGAA 2022 section 2. Okay. Diagram shows that there is mass 2.4. Okay, so I'm just gonna think about the forces. We already know it's an equilibrium. So I'm gonna think about the forces. We've got this 36 newtons here. We got this force F at an angle theta. We got the weight mg, and then we've got the normal contact force N, and we know it's smooth, so there's no friction. So here we go, resolving. Yeah. So if we resolving forces, what's it called? Horizontally. This is the notation I like to use sometimes. We get, because it's not moving horizontally or accelerating. It's not accelerating horizontally. We know that the forces have to cancel out. So that 36 newtons has to equal this horizontal component. Has to equal this horizontal component of F, as in this. So that's going to be 36 has to equal F cosine theta. Okay, which is good to know. And then if we resolve forces vertically, we get, what's that? N has to equal mg. The mass is 2. So mg. I'll plug in numbers later. Mg plus F sine theta. Okay. So to get F sine theta, we're given that tan theta is 4/3. So F sine theta over F cos theta equals tan theta, right? So that implies F sine theta equals 4/3 times 36, which is 48. Therefore, N equals 2.4 kilograms times 10 newtons per kilogram plus 48 newtons, that's in newtons. And that's going to be 24 plus 48 newtons, which is 72 newtons. So that is E. Okay. Length of a spring when no force acts on it is L. The spring constant of the spring is 3 times 10 to the 3 newtons per meter. Okay, on a accelerating spring supports 30 kg mass. Okay, so we'll call that acceleration A. Okay. So we know this, the floor of the lift is accelerating down. Okay, we'll define X. So let's say this is the original, I'm just guessing, let's say this is the original length. And let's say the spring is extended. Now we'll define X as the extension, so it's positive when the spring is extended, negative when not. So what's going to happen here is that so I'm going to draw like I know it's confusing because I have to find, let's pretend X isn't the name of one of the coordinates, but let's say this is the y-axis. We'll define this y-axis is going to be fixed relative to the Earth, so it's not going to change its position relative to the Earth. So although this lift is accelerating, this is going to stay fixed in position, like assuming that we're just standing on the Earth and not moving about and accelerating with the lift or anything. So we're outside. So yeah, anyway, that's, yeah, okay. And then I'm going to define this the height of bottom, that is y1, and the height of the lift is y0. And yeah, so what we'll get, yeah, we can start thinking about this system. So what forces are acting on this mass? Well, it's got its weight mg acting downwards, and it's also got the force from the spring kx, which acts in the opposite direction. So in this case, in the diagram I drew, x is upwards, so the force from the spring is pulling it downwards, so it's going to be kx. And yeah, those are the only two forces acting on the spring. So yeah, if we look at the forces on the mass, we get, so net force equals mass times acceleration. So the net force is going to be minus mgj j hat minus kx j hat. Yeah, sorry, I'll redo that. So we know then net force equals the mass times the acceleration. So that's going to be weight plus the spring force, which we'll just call F, equals ma. And the acceleration, is the second. So the position in this fixed reference frame, the position of this of mass is given by y1j. So its acceleration is going to be, well, I shouldn't really use a because I've already used it here, but anyways, it doesn't matter. Hopefully you know the difference. Okay, we'll call it a prime. So a prime is going to be just the second derivative of that this vector, y1j, which is that. The weight is going to be have magnitude mg, direction downwards, so it's going to be minus mgj. So we'll say the force from the spring is going to be minus kxj. And then we can check this makes sense because when x is positive, k is always positive. When x is positive, the direction of F is going to be downwards. So when x is positive, this spring is extended, so yeah, it's upwards like that. And the direction of F is going to be downwards, which makes sense. And then the opposite is true. So when x is downwards, so the spring is compressed, the spring is going to push upwards. So yeah, this makes sense. We didn't get our signs mixed up. So yeah, then we put it all together. Then what have we got? We got minus mgj minus kxj equals y1j. And that must mean that minus mg minus kx equals, yeah, the second derivative of y1. So what we're aiming for is we're aiming for an equation that has no y1. We only want x because x is the only unknown. We just want to think about how the extension varies, because that's basically what this is asking. What is the difference between L and the length of the spring when? So yeah, that's pretty much just another word for x, the extension, the way to say x. So we're going to try to find an equation linking x to y1. So I can see one. So we've got this distance over here, which is that. It's always going to equal L plus x, because if x is positive, so over here I should x is greater than 0 in this case, this diagram also. So if x is positive, then the length gets added, but if x is like that, x is negative, then L plus x is going to be this length. So it works. Remove that. So yeah. So this is true. I hope you can see that. And we always know y1 is going to be greater than y0 because the mass is never going to go. The mass will never go like this. It will never go below the lift or anything. That's impossible. So we can say y1 minus y0 equals L plus x. Then what I'm going to do is take, because these two, this is true for all time. It's true for all time. For any time we look at this system, this equation is going to be true. What that means is its derivative with respect to time is always going to be, like if we take the derivatives of both sides with respect to time, the equation is still going to hold. Remember, L is constant, so it won't change over time. So its derivative is 0, and then we get x dot, and then we'll do it again. And we also get this. Okay. And then one thing we can notice is y0, the second derivative of y0 is basically the acceleration of the lift, but in the opposite direction. And we know it accelerates downwards at a. So all that to say that y0 equals minus a g. Oh, sorry. So that means therefore y1 equals dot plus a. Is it plus a? No, sorry, minus a. Got my signs confused. Yeah. Okay, and nice. And now we can substitute this into here, into this equation over here, and then we'll get minus mg minus kx equals x dot minus a, and then if we get everything to one side, we get x dot minus kx. What am I talking about? I forgot to write the m over here. Yeah, because it's mass times acceleration, so sorry about that. So this should be m. Now I'm doubting whether it's a minus g. Yeah, so we get this which is actually a second order differential equation. And then if you look in, if you do further maths and you look into Corpure 2, this is a second order non-homogeneous differential equation, and it'll explain to you how to solve it. But basically the general solution, I won't go into that right now because I don't know, it's kind of like a method that you just memorize, so there's not much to explain, it's just following a method. Because, okay, but I can just kind of quickly summarize it, even though this will make no sense if you haven't memorized the method. And even if you have memorized the method, it won't make any sense why you're doing this. You just do this, so don't worry if this is a weird part. It's still weird to me, like it's just a method I've memorized, but I've got no idea why it works. Again, if you do maths, you'll probably understand it at some point. But the equation you're supposed to look at, the corresponding quadratic equation you're supposed to look at it is this. yeah, equals 0. And then that's got, because k over k and m are both positive, that's got complex solutions, which are these. And then the general, so that means the complementary function is going to be this, in this form, e to the real part of u. The real part of u is 0, so e to the 0t. And e to the 0 is just going to be 1, so the e part goes away. So it's not actually a decaying or a growing sinusoid, so it's going to be c1 sine root k over mt plus c2 where c1 and c2 are just arbitrary constant, like the constant that depends on like initial values and stuff like that, parameter conditions. And then you can always, I don't know where you learn this, in which maths textbook you learn, maybe in pure, maybe in core pure, then you can always rewrite it in this way. So it's just it's actually very, when you add a scaled sine and a scaled cosine, any linear combination of sines and cosines is just going to be a scaled and translated sine or cosine wave, which is a kind of surprising fact. Like, it doesn't feel like it should work at all. So, but it's good. It's a nice fact. So over here a and phi are just two constants. So anyway, so the complementary function is that, and then because this part a minus g is a constant, the what's it called? The particular integral, I think it's called, or I don't know what they call it. But the thing you add to get the general solution, you get the complementary function plus some constant gamma, let's call it. And yeah, so that's what our general solution to this situation is going to. So if we just sketch that out, what that means is basically over time, let's see, gamma, if we think about this, like gamma can't be negative, it's always going to be positive, because, and a can't be greater than gamma, because this is what the graph is going to look like. X is basically going to just oscillate around gamma. It's not going to change length. I think you can interpret that because there's no like frictional force or anything. But yeah, this is what the function of how x will vary over time. And then, but notice over here, it just kind of asks for one value of x. What is the value of x as the lift is accelerating downwards? It doesn't tell you anything about like at what time, or So what I'm guessing it means is, what is the value what is the stable value of x? So i.e., we could have a case, it could easily be like if the initial conditions are just right. So what that means to me is that the lift and the mass, so what, like, okay, I'll explain later, but so if the initial conditions are right, and if a equals 0, x is gamma, so it's this constant, it doesn't vary over time. So the extension, yeah. And I think that I haven't actually like saw what the initial conditions would have to be, but just from like a physics argument, I think what it would have to be is that I haven't actually worked out if the spring's going to have to be extended or compressed yet. So I'm just going to guess. I think it's going to be compressed. But that all depends on the values of k and m and everything else. So if this is gamma, if the extensional compression is gamma, these are the initial conditions for x not to vary over time. What we've got to have is that the mass is also starts off with the same with this compression or extension gamma, and it moves with the same acceleration as the lift, and it also moves with the same velocity. So they're always the same. This distance over here is fixed basically, and it's fixed in such a way that that gamma and it's fixed in such a way that the compression or extension of this spring is gamma. So yeah, that's my idea for how you'd get this stable, how you'd get X to be stable. So I'll just write that down. I'm guessing the question asks find gamma basically, so the value of extension, that if everything else is right, X would be like, if the conditions are right, what would the stable value of the extension be? So yeah, so anyways, when X is constant, when the extension is constant, so when the extension X is constant, what do we get? We get X dot equals 0, which implies X double dot equals 0. So from here you get y1 double dot equals minus 8. So what that means is, this also accelerates with acceleration a. So then we can look back at, which equation was it? It was this equation over here, and we get minus mg minus kx equals minus ma. So that means that m times y a minus g equals kx. So x equals m times a minus g over k, and plug everything in. 32 minus 10. So anyways, I know everything is in standard units. That's kilograms. Yeah, everything's in standard units. And k is, what is it? 3 times 10 to the 3 meters per meters. So because everything's in standard units, so is x. X is also going to be standard units. So then we get 8 over 10 to the 2, which equals 80 centimeters. Sorry, 8 centimeters. Because that's 80 over 10 to the 3 meters, which is 80 millimeters, 8 centimeters. So yeah, we go. So I hope you read the question. So the setup is like this. So I'm going to use resistance. I'm going to use ideal wires in this, what's it called, in this diagram. And I'm just going to use resistors to model the resistance of the wire. So let's see. The wires are, the current in here is I. It's got a voltage ratio of 5 volts, and it's a step down transformer. So the secondary coil is going to have a voltage of V. And yeah, anyways, it supplies a power P, let's call it, which is 40 kilowatts. So we know V is 250. We know that is P. We know this is R. And yeah, So we're trying to find out what's the rate at which electrical energy is transferred to thermal energy in the overhead cable. So I'll call that heat, P heat. We know that's going to be I squared R. Because it's just the power dissipated by these two resistors, basically. So, well, we need to find I. We can use the fact that this is 100% efficient. So the power being outputted by the primary coil is going to be equal to the power inputted transferred to the secondary coil. So that's going to be I times 5V equals P. So I is P over 5V. Therefore, P heat equals, this resistance is 2 I squared R, because we've got two resistors in series. So what's this? This is going to be, P heat is going to be 2R times by P over 5V squared, which is going to be 2 times 2.5 ohms times P is 40 kilowatts, which is 4 times 10 to the 3 watts over 5 times 250 volts squared, and that's going to be in standard units, so we're just going to end up with watts. So what do we get? We end up getting, so that's 5, we can do some cancellation over here. So let's take out factor of 5 there, so that's 8. Take out factor of 4, of 250, sorry. That's going to be 5 times 32 squared watts, which is going to be so like that, 160 times 32 watts, which is going to equal 480 plus, what's that? No, 4,800 plus 320 watts, which is going to be 5,120 watts, which is 5.12 kilowatts. A wave particles in medium, particle in the medium, zero displacement from 1.12 second intervals, and at no other times. Okay, so what this means is that so if we imagine sketching the displacement versus time of this, and this is a full time period, well, it has zero displacement every half time period, so that means half t equals 0.12 seconds. The wavelength of the wave is greater than 10, okay. 2 points are 5 meters apart along the direction of travel. Phase difference between the two particles at the same distance is pi over 3. Okay, so I see what they said. The 2 points are 5 meters apart. Is just because, then these 2 points are on the same wave. They're on the, I don't know how to describe it, like they're in the same cycle. So what we can say is that, so let's call this x, and we'll call that phi. So x over gamma equals phi over 2 pi. Yeah, so the ratio of the distance separating the 2 points to the wavelengths is the same as the phase difference between them to the to 2 pi radians because yeah, the one full cycle you go through a full wavelength, and you also go through 2 pi radians in terms of phase. Yeah, I think that's more so just how phase difference is different. So I think you can take this as more of a definition, not as something that is like derived from something else. But I think this is more of a different. Anyways, so you're going to use that to find when you want to find the speed. So you got the time period and we got the wavelength. So we got the wavelength, which is 2 pi x over phi. And v equals f lambda, which equals lambda over t. So v equals 2 pi x over t phi. And it is going to be 2 pi times 5 meters over t, which is 0.24 seconds, times 5, which is pi over 3. So v is going to be 10 over 0.08, this is going to be 10 to the 3 over 8, 0.25 to 10 to the 3, so 125 meters. Oh, what is that? Yeah. Okay, so we've got 3 identical springs. Let's call their spring constant K. Okay, they're connected in series as shown. Downwards force T is applied, and then one of them is cut up into 4 parts and arranged like that, and F is applied to the bottom. And the 2 extensions are equal. Okay, and they obey Hooke's law. Nice. Okay, so let's call the extension X. So over here, this spring is also going to experience a force T. You can think about that in this way. So basically, what happens is that if we think about this spring over here, it's going to have a force T downwards, and we assume it's massless. So to remain in equilibrium, it needs to have a force T upward. That's put by this spring above it. And because of Newton's third law, that means it puts a force of T downwards. If it puts a force T downwards on the spring above, so that spring above is also going to feel a force T. So the total extension is going to be the extension of each of them, and extension of a spring is the force over the spring constant. So that's going to be 2 times T over K, which is 2T over K. Spring R is okay. So now we need to find. Let's say they have a spring constant K prime. So now we can use the same reasoning about forces and stuff to reason that the force on each of these springs is going to be half F over 2, and the same up here is going to be F over 2, because these two rods have to be in equilibrium, and also because of Newton's third law. You can think about it for yourself, like I won't explain it fully, but you can think about why. And then the extension is going to be the extension, the sum of the extensions of these two layers, which is good. So the extension for this layer is just going to be the extension for this layer is just going to be the extension of one of these springs, because they both extend the same, because this is applied at the center. So both experience the same force, because there's no torque, no turning moment about the rod. The reason, because if it's applied at the center, then there's that symmetry. So you get both, both experience the same force. So both extend the same amount. So the extension is going to be X, which equals the extension of the first layer, which is F over 2 over K prime. That's the extension of one of the springs in the first layer, plus the same for the second layer, so that's times 2. So that's going to be F over K prime. Now we just find K prime in terms of K. The way we can do that is by thinking, let's imagine we got, let's say, R before it's cut up, and then R after it's cut up with all the pieces attached together. So if we apply a force F downwards, and then we get an extension, let's say y. So then we know f equals ky over here, in this one obviously because of Hooke's law. But over here, the extension y, so sorry, this means y equals f over k. So the extension over here is going to be the 4 times the extension of each of these individual smaller parts, and each of these smaller parts is going to extend by f over k prime. So that means y is going to be 4f over k prime. So what that means is that k prime has to equal 4k. So therefore, x has to equal f over 4k. So equating these two, we get 2t over k equals f over 4k. So t equals f over 8, which gives us b. Okay, a nylon cube resting on horizontal surface is volume 64 centimeters cubed. So let's call the side length L, so that means the side length is going to be 4 centimeters, which is 4 times 10 to the minus 2 meters, together in standard units. Force F is applied vertically down as the top face of the cube, so you compress the height by x. After the variation of F by x, where's the Young modulus of the nylon? Okay, so Young modulus is going to be the stress over the strain, which is the force per unit area, which is just pressure, really, over the extension over original length, which is going to be, I always remember it's flower over axe, like peace over hate, love over hate, peace over war. Anyways, so in terms of the variables we're using, that's FL over L squared x, which is F over Lx. So that means F equals ELX. And then we've got an F against x graph over here, so that means the gradient of it, which is df by dx, is EL. So we know this, we know L. So the Young's modulus is going to be df over dx times 1 over L, which is df over dx is going to be 150 newtons up here with this change over 1.25 times 10 to the minus 6 meters. One over L, which is times 1 over 4 times 10 to the minus 2 meters. We get it in pascals. So we get that's going to be 1.5 times 10 to the 2 over 1.25 times 10 to the minus 8 times 4 pascals, which is going to be take out factor of 0.25 and each of these we get 6 and 5, take out factor of 2. So then we get 3 times 10 to the 2 over 10 times 10 to the minus 8, which is 3 times 10 to the 9 pascal, which is F. 5 lampposts along a straight road are positioned at uniform intervals of 60 meters and moved by traveling at constant pace. Passes the first. Okay, we have to be careful. Passes the first lamppost. Doesn't. Yeah, okay. So that means if it passes 5 lampposts, it's actually gone the distance between 4 lampposts because it starts at the first and it ends at the 5th. So let's call the motorbike's velocity W. So W equals 5 times 60 meters over, no, sorry, I just made a mistake that I tried to, it's got, there are 4 intervals here. So mark that one. There are 4 intervals between these 5 lampposts. So 4 times 60 over 20, which is going to be 12 meters per second. And then a car traveling in the same direction as the motorbike is accelerating at 6 meters per second. Times t equals 0. At the first lamppost at a velocity of 3 meters per second. What time? Okay, so when overtake happens, we got the distance traveled by the motorbike is going to be the same as the distance traveled by the car, which is accelerating. So I've used that Suva equation. U over here is 3. So anyways, rearrange. So plugging the numbers in, we get 12t equals 3t plus half times 6t squared. So that's 9t plus 3t squared. So t squared minus 3t equals 0. So t equals 0 or 3. So we'll take the 3-second solution. Okay, so an electrical appliance has an input power P, which is a function of time. So this is the power. Okay, so we know the power wasted is going to be 1 minus 0.9 times P, which is 0.1 P. And the power wasted is the rate of change, the time rate of change of the energy wasted. So therefore, there is in the energy wasted from time t equals 2 to t equals 3. It's just the integral of the power wasted, which is 0.1 p with respect to time. That's going to be 0.1 3t squared plus 4t. This is going to be increase the power by 1 divided by the new power. Zero point 1 plus 127 plus 2 into 2.9. So yeah, 2.9 joules. Okay, a solid cylinder is made of a transparent glass refractive index. Let's call that N. An ray of light traveling in air hits the cylinder at the center of one of its circular faces. So it hits it up here at an angle theta, and then refracts as it enters. So when it refracts, we know the angle of refraction is going to be smaller. Let's call this R. That's going to be smaller because glass has a higher density, so light moves slower. And then it strikes the curved surface. So let's say this is going to be 90 minus R at the critical angle. So that means it exits at 90 degrees. So what that means is that, let's call, this is N. So that means, using Snell's law at the second refraction, we get N sine of 90 minus R equals 1 sine of 90, which is just 1. And so that means N cosine R equals 1. And then at the start, oh yeah, so that means and at the first refraction, so that's the second refract. First refraction, we get 1 sine theta equals n sine r. So that means, yeah, and then from this one, let's call this, from the equation for the second refraction, we can get cosine r, which is going to be 1 minus sine squared r, because the square root of that equals 1 over n. And that's because cosine r is going to be positive, because r is going to be less than 90 degrees. So that means 1 minus sine squared r equals 1 over n squared. So n squared minus 1 over n squared equals sine squared r. So that means sine of r equals root n squared minus 1 over n. It's going to be the positive root because, yeah, again, r is less than 90 degrees, so sine is positive. So that means, therefore, sine theta equals root n squared minus 1, which is going to be, so n squared is going to be 4/3. So it's going to be equal to root of 1/3. So theta is going to be the arc sine of 1 over root 3. Yeah, that's good. What is the magnitude of impulse on the object over this time interval? So impulse is the change in momentum. And for constant mass, that's going to be the mass times the change in velocity. And yeah, we can figure out the velocity function over here by differentiating that. So the impulse is going to be the mass, 20 kg, times the change in velocity, which is, so it ends at t equals 1. It's going to be minus 3 minus 6. And it starts at t equals 0. So the velocity is going to start off at 0. And that's in meters per second. So what we get is minus 180 kilograms meter per second. So yeah, that's the magnitude, 180. Two small hard spheres of mass m and 2m are suspended side by side from light vertical string. Swing through 90 degrees and strike the smaller sphere. The two spheres stick together and rise to a maximum height h. So we want to find h in terms of, okay. So at first, what you might be thinking is you can conserve energy between here, between like at the start when this is all the way up here. Sorry, I'll do non-permanent. You can conserve energy between here. It swings down, collides all the way to here. You could say energy is conserved from there to there, but that's not necessarily true because of this collision. Like energy will be lost as sound, as heat during this collision. We don't exactly know. Yeah, basically we know that energy is going to be lost because it's an inelastic collision because the two balls stick together, so there's definitely going to be energy lost. So what the general idea is here, we can conserve energy between here and here to see how much kinetic energy, or like to find out the velocity that this 2m ball will hit this with. Then over here, to figure out the final velocity of these two, we can conserve momentum because that's always conserved. And then from just after when they start sticking together to here, we can conserve energy. So we'll do that first. So let's call this, we'll call that A, that event, B, and then C. So conserve energy A to B just before. Actually, I'll write that in. Yeah, I'm just making up this notation. A to just before B. So we got these labels for the events. So change in gravitational potential energy equals the change in kinetic energy. There's no other energy transfer is equal to 0. So that means it loses minus 2mgl, and it gains, let's say the 2m ball, it gains it has a velocity of u by the end of it. So half 2m u squared equals 0. So that means mu squared equals 2mgl, so u equals root 2lg. And then conserve momentum from just before B to just after V. So let's say that they end up moving at a velocity. So initially the momentum is 2mu plus 0. Find pass at the end of 3m, and let's say they move with a velocity v. So that means v equals 2/3 u. So what does that mean? Then we can conserve energy again, just after B to C, and then we get, that's going to be the change in kinetic energy. It's going to lose kinetic energy. It's going to gain gravitational potential energy. The combined 3m mass. So it loses all its energy because over here it's going to have no speed. It's going to like you can notice it's going to go and then it pauses for a minute there, so it's going to have no velocity, no speed. Yeah, no speed or velocity. Okay. Anyway, so it's going to lose all that, so that's going to be minus half 3m v squared, and it's going to gain 3mgh equals 0. So that means we can, if we rearrange it, we get h equals v squared over 2, sorry, let's move that up. Let's see what was over there. So that means h equals v squared over 2 g, which is going to be, what's that, 4/9 u squared, which is going to be 2u squared over 9g, which is going to be 4lg over 9g, which is going to be 4/9 L. Let's see. 3 resistance wires X, Y, and Z made from the same metal connected to each other and it's into a circular plastic ring as shown. Wires X and Y have twice the diameter of wire Z. Wire X is 12 centimeters long, wire Z is 15 centimeters long, and is connected across the diameter of the ring. Because that means this is 90 degrees because of the circle theorem. Power supply is connected to the 2 corners of the triangle that lie in the diameter. Okay, so it comes in like that. Okay, so the resistance of Z is going to be resistivity times its length, which is 15, R equals rho L over A times this area, which is going to be is pi R squared. Let's say R is its radius. And then so X and Y are in series, so they can just be treated as one entire wire. So we need to find the length Y. So we can use what's it called? Pythagoras theorem. So Z squared. So this is in terms of length. Z squared equals X squared plus Y squared. So Y equals root Z squared minus X squared, which is root of 15 squared minus 12 squared. Wait, I'll move that over there actually. Right. Dang it. There we go. So Y is going to be root 225 minus 144, which is root 81, which is 9. So that means if we think about the resistance of combined X and Y wire, it's going to be resistivity times, what is it? That is, the total length is going to be 9 centimeters plus 12 centimeters times 21 centimeters over pi, and it's got X and Y each have twice the diameter of Z, so it's going to be 2r squared, which is going to be that, which is the root of 21 centimeters over 4 pi r squared. So that means Rxy equals Rz over 15 centimeters times 21 centimeters over 4, which is going to be, cancellation, take out factor of 3, 7, and 5. So what's that? Okay, and then you can cancel out the units as well, so it becomes dimensionless. So you get 7/20. Oh, dang. 7/20 Rz. So yeah. And we want to find the ratio of the current in X to the current in Y. So we know the voltage is going to be the same across both of them. So using Ohm's law, that means that Ix Rxy equals Iz Rz. So Ix times by 7/20 Rz is Iz Rz. So these can, oh sorry, not all of it. So just the Rz's, just the Rz's cancel. So then we get Ix over Iz equals 20 over 7. That's G. And 13, a light rope is cross-sectional area, this, which we'll call A, and unstretched length, this, which we'll call L. Rope is fixed horizontally between two supports that are 0.24 meters apart. When its 1 kilogram mass is suspended from the middle of the rope, vertical displacement in the middle of the rope, vertical position is X. Okay. We've got that. So this is, let's say this is the rope. Well, that's not very accurate. So this distance over here is X. Okay, and then this distance at the top we'll say 0.24 is 2d, so this is d. And then let's say this angle over here is theta, so this is also theta. So anyways, so we know that, actually no, let's use a different, we won't use x because that will confuse us with the extension of the rope. Let's call this d, and let's call it h then. So what we know is that, and there's also, what's this? 1 kilogram mass, we'll call that m. So we've got force mg acting down over here. So we know that this part of the, if we zoom in on this part of the rope, it's going to be in equilibrium. So if I draw it over here, we've got mg acting downwards, but we've also got the tension in the rope from either side, an angle theta. So that means equilibrium, therefore, so if we resolve the forces vertically, that we get 2t, that's going to be sine theta equals mg. So t equals mg over 2 sine theta. And then we can use that formula for the Young's modulus, which is going to be Young's modulus is stress over strain, which is force over area over extension over length, which is going to be, so let's call the tension F just to be clear. So that's FL over AX, which is going to be, as we see from here, MGL over 2AX sine theta. And the only unknown we have over here is X, which we can get by, so X is going to be, so let's say this distance over here is R. So R squared, because of Pythagoras, equals H squared plus D squared. So R equals root H squared plus D squared. So the extension is going to be the new length, which is 2r, minus the related length, which is 2d. So that's going to be 2 times root h squared plus d squared minus d. So that this is what we get. We get this. Oh, and we also want theta, the sine of theta. We can also use that. Oh, actually, this might end up being quite nice, actually, or maybe not. Okay, let's not. Actually, we'll leave that there. So, and also let's think about what sine theta is going to be. So sine theta from this triangle, we can see that sine theta is going to be h over r. So therefore, x, anyways, so we can put everything together, and then what we get is that E equals mglr over 2axh, which is going to be not very nice. Oh, the original length is 2d, yeah, sorry. Yeah. Dang it, so that's going to be, okay, which is going to be, sorry, mg dr, cancel the 2 over AXH. Which is going to be MGD. So that's going to be R is what? Root H squared plus D squared over 2 AH times by root H squared plus D squared minus D. So that's what the expression we got. And then putting all of that in. So anyway, it's 2D. So that is 0.24, so D equals 0.12 meters. So you can just plug it in. Actually, maybe this was a bad idea doing it this way. Yeah, actually, I think I should have just plugged in numbers first. Like maybe it would have been way easier to just calculate theta. Actually, you know what? I don't think it would have been easier. I think it's just going to take, because like without a calculator, how in the world are you going to calculate arc sine over angle? So I think it's very nice, and it was going to, what's that? It's going to be 12 over 5. Oh, you know, actually, okay. Anyways, this is quite good. So we know if I add a page. So anyways, the R, which equals root H squared plus D squared. So anyways, if we, I won't do it like that. If we draw out that triangle, R, H, and D, where D is what? 0.12 meters, which is 12 times 10 to the minus 2 meters. And H is what is 5 times 10 to the minus 2 meters. And then R is going to be, we can say 12 squared plus 5 squared times 10 to the minus 2 meters, which is going to be 144 plus 25 is 169 times 10 to the minus 2 meters, which is 13. So that's going to be R. So if we plug that in, what we get is E. M is 1 kilogram. G is 10 newtons per kilogram. G is what? Times 12 times 10 to the minus 2 meters times R, which is 13 times 10 to the minus 2 meters. Then 2A is what? A is 6 times 10 to the minus 8 meters squared. And then H is times 5 times 10 to the minus 2 meters times what? R minus D, which is going to be 13 minus 12 times 10 to the minus 2 meters. Then anyway, we get cancel out all the, so we can do some cancelling. So that's going to be, there's going to be 1, so we don't have to worry about that. We also don't need to worry about that. Take out the 2 and the 5, can take out that. Take out a factor of 6 there, so we get 2. So what we get left up with is 2 times 10 to the minus 2 times 13 times 10 to the minus 2 all over 10 to the minus 8 times 10 to the minus 2 times 10 to the minus 2. pascals. Anyway, we can do some more cancelling. Those 10 to the minus 2s. Get rid of them. So what we have is 26 times 10 to the 8 pascal. See if that's an option. Yeah, 2.6 to 10 to the 9 liters per meter squared. Three graphs show the displacement, velocity, and acceleration against time from an object moving in a straight line. So anyways, so displacement, velocity, and acceleration, they're all just the they're all just linked by a single time derivative. So there's going to be, these graphs are just going to be the gradient graphs of each other, basically. So the first thing I've noticed is that Q could be the gradient graph of R. Because look, R starts with a negative gradient, and Q starts negative. And then R goes to zero gradient. Exactly, sorry. Kind of missed that. When Q goes to zero, R goes to no gradient, and then Q goes positive for all this region, and the gradient of R is positive for all this region. And then it goes negative afterwards. So I think if we label R as Ft, then I think Q could easily be probably just like F prime T. Well, we know that P isn't going to be F prime T because look, R starts with a negative gradient, but P starts positive at time equals 0. So that's definitely not going to be that. Now we just have to find the link between P and so P can either be F double prime T or the integral of what's it called, of R, in which case R would be the derivative. So let's see which one of the options it is. So okay, so Q, I'll do a bit in red. So Q starts out with positive gradient, P starts out positive. Okay, and then Q's positive gradient, I guess, decreases. Q's positive gradient decreases, which it shows over here. But over here, P predicts that the gradient of Q is 0, which it isn't over here. So P can't be F double prime T. So it has to be this. Let's think about if that's reasonable. So in this case, R would be the gradient graph of P. So P starts out with, I'll just rub out these that I've made. So we'll do it in blue this time. So P starts out with a negative gradient, which R shows. And then the gradient decreases, and then P reaches a place with 0 gradient, which R also shows. So the gradient decreases till about here, gets more and more negative, and then at some point, which R predicts over here, the gradient starts becoming more positive again. So less negative until it reaches 0 over here, which is true. And then the gradient starts to increase until it reaches a maximum around here, and then it decreases again, but it's still positive. So yeah, P looks like it's going to be big F of T. So if we put that all together, that means that P is going to be the lowest derivative of time, so i.e. displacement, and and then r is going to be the next, which is velocity, and then there's acceleration. Oh no, sorry, dang it. So r is the velocity, it's the next derivative of the displacement, and q is the acceleration. So a system of light springs that does not obey Hooke's law has an unstraight length of 2 meters. The extension x of the system is related to the force applied to it by F equals px squared, where p is a constant. A force of 2,400 newtons increasing the length of the system to 2.2. How much work is done increasing the length of the system from 3 meters to 4 meters? Okay, so when it says how much work is done in increasing the length of the system, that basically means how much, the work that's done in increasing the length of the system is transferred to, what's it called, elastic potential energy. So that's basically because we're just assuming that we're pulling it, we're extending the spring. If this is the spring, and F is the spring force. So if we extend it by x, then it puts back a force F that varies with x. We're also pulling with a force F of x, because otherwise, if we pull with a greater force, then we'll be accelerating the spring, and we'll be transferring into the kinetic energy. The work we do goes into kinetic energy, as well as we'll be doing more work, and the extra work that we do will be going into kinetic energy as well as the elastic potential energy. So we're only concerned about the work that goes into elastic potential energy. So, and that work is going to be, we can calculate it by imagining what happens when we extend the spring by only a little bit, let's say dx, and over this period we can say that the spring force F is approximately constant, and that gets truer as dx goes to 0. So the amount of work that we do is going to be dw equals F dx, because the force we apply, F, is going to be in the same direction as the as the displacement, because the displacement of the spring is going to be in this direction. So F dx is going to be positive. And we do positive work because we're doing positive work on the spring. So anyways, to get the total amount of work done by increasing the length of the system from 3 meters to 4 meters, that basically means increasing x. Over here x is 1 meter, and then x becomes 2 meters, so we have to integrate this. So sorry, let's call that total work done, the integral of F dx from x equals 1 to x equals 2, which is going to be p times the integral of x equals 2 equal x squared dx. So if we call this the top work, or let's call it work done. And that's going to equal which is going to be p times by which is going to be 7/3 p. So we just have to find p to be able to solve this, and we're given that when the force is 2,400 newtons, when we extend it by 0.2 meters, the force is going to be 2,400 newtons. So that means P equals 2,400 newtons over 0.2 meters squared, just 5 squared, so it's 2,400 newtons, which is 0.25 times 2,400 times 100, newtons per meter squared, Pascals. It's going to be 600 times 100 pascals, which is 6 times 10 to the 4 pascals. That means the work done equals 7/3 times 6 times 10 to the 4 pascals, which is 14 times 10 to the 4, joules, because this 7/3, if we get the dimensions right, is going to be in meters cubed. Yeah, x cubed, the dimensions of x at meters, length is length. The units of x at is meters, so the units of x cubed over 3 is going to be meters cubed. So yeah, this is going to be in joules because we got everything in standard units. And then what do we get? That's going to be 140 kilojoules. So yeah, that's E. Okay, we are trying to find the reading on the ammeter. Okay, let's label everything. We're just going to apply first and second Kirchhoff laws. And let's call this current over here I. And let's call this current over here J. I'm just choosing any direction for them. This is going to be I plus J. Okay, let's do the first loop that we're going to take the voltage law around. Is going to be, let's see, starting from there, going all the way around and back. So that's going to be minus 18 volts, because when we go this way, if we were to go this way, we'd gain plus 18 volts, but since we're going the opposite way, we'll lose 18 volts. So minus 18, and then minus 20i, because we're following the current across the 20 ohm resistor, and then plus 4j, because if we went that way, it would be minus 4j if we went with the current. But since we're going the opposite way to the current, we gain going across this resistor. We go up a voltage step. So anyways, so that's all going to equal 0. Then let's rearrange that anyways. So that's one equation. And now the second loop, let's do this loop. So that's going to be minus 4j. What's the next one? This is going to be plus 20 volts, plus 20, and then minus 8i plus j equals 0. So that means 20 minus 8i minus 12j equals 0. Then from this blue one, we get that 4j equals 20i plus 18. So 12j equals 60i plus 54. So that means from this one, so if we combine both of them, we get 20 minus 8i minus 60i minus 54 equals 0. So that means minus 34 minus 68i equals 0. So that means 68i equals minus 34. So I equals minus a half. So the reading on the ammeter is going to be, this is going to be half an amp, and the current's actually going to flow this way. So yeah, that is E. Okay, so here we go. Upper diagram shows the equilibrium positions of 9 equally spaced particles in a medium. The lower diagram shows the positions of the same amount of particles in a longitudinal wave. It's like sound, so it's like compressions and rarefactions. Traveling through the medium. The wave is shown at time t equals 0. Traveling to the right. Okay. The frequency of the wave is 0.5 hertz, so f equals 0.5 hertz. So that means t equals 2 hertz. So which graph represents the displacement of the particles at a later time t equals 0.5 seconds, which is, so we want to find what's happened after a quarter time period, basically. So let's think about what this is at t equals 0, right? So we're going to think about what happens at t equals 0. Well, what's happened is that we've got there's no displacement over here. because this is the third one, look, and it's in the same position. And then where else is there no displacement? This one, this one, this one, this one, this. There's also no displacement here. Okay. So I think that's enough to figure out what happened. So let's say positive displacement is, yeah, positive displacement represents particle displacements to the right. So this is going to be positive displacement. So at t equals 0, this is what the graph looks like. At t equals 0, we've got this. If this is the displacement, and this is time. We've got max displacement. Oh no, sorry, distance. And that's 2. And then where else? 6. So there we go. That's what the graph looks like. Yeah, because over here all these ones are displaced to the left. Like this has got the biggest displacement over here. So that makes sense. So this is what it looks like at t equals 0. And the frequency of the wave is 0.5 hertz. Which graph represents the displacement of these particles at a later time? T equals 0.5 seconds. So after a quarter of a time period, that means, yeah, every particle is going to be a quarter of the way through the cycle. The wave is shown at time t equals 0. It's traveling to the right, so the wave is going this way. That's the direction of the wave. So yeah, after a quarter of a cycle, let's draw it in blue. So after a quarter of a cycle, 2 is going to be at the maximum now, and then 4 is going to be, there's going to be no displacement at 4, and 6 is going to be the lowest. So it's going to look like this. So let's look for that. So this is at 0, 2, 4's got no displacement, 6 has got max negative displacement. Yeah. This is what it's going to look. So it's going to be A. 17. That's a bit of a tough one. You need to think about that one well. This is the internal resistance, small r. This is the pure cell, pure EMF. Yeah, that's the external resistance R, your current I, and then this is the cell with the internal resistance. Okay, so we've got the efficiency, we would define it as power dissipated by the external resistor, that's I squared R, over the power supplied by the pure EMF, which is I epsilon. That's IR over epsilon. And then we know, because of Kirchhoffian, epsilon minus IR equals 0. So epsilon equals I times R plus R. So I equals, I over epsilon equals 1 over R plus R. So E is R over R plus R. Another way of writing that is 1 minus R over R plus R. So now let's think about what this, because this is a function, because R, the small r is just a constant. So now let's think about what function the function E looks like as a function of R. So this is what, so if I draw some axes, this is a very useful tool actually. So anyways, this is what Okay, this is what. If this is, this is y and this is r. This is what y equals 1 over r looks like. And then y equals 1 over r plus r is just going to be a translation by minus r in the x direction. So it's going to be that, literally just that. So that's a translation by r in the x direction, by minus r in the x direction. So actually we can make that a different color. Let's make it red. One over r plus r. And what's this going to be? When r is 0, that's going to be 1 over r. And then if we then do y equals 1 over, if we multiply that all by little r, then what we get is this. Basically stretch it up. So basically the stretching doesn't really work just by doing it like this, because it just stretches around the bottom. So you see that bottom is fixed, when in reality it should be that the x-axis is fixed, not this. We're going to move it up like that. But anyway, the asymptote is still. This x-axis is still the asymptote here. Oh, dang it. This x-axis over here is still the asymptote, or r-axis even. So this is what. Sorry. That's what's y equals r plus over r, big R plus small r is going to look like. And this is going to be 1. When big R is 0, y is 1. And then if we flip that over, so then if we think about what this graph looks like, this is what what's it called? What y equals. Sorry, I'm kind of confused about all the colors. This is y equals minus r over r plus r. So this is going to be minus 1. We reflect it in the x-axis. And then if we add 1 to it, this is what we get. Let's make it maybe purple. Make it blue. This is what we get. So the asymptote over here is still y equals 0. So if we add 1, the asymptote is now going to be y equals 1. So sorry, that is the asymptote. Y equals 1. Then this is going to be y equals 1 minus r over r plus r. And then that is just this graph. And you can check, because when you plug in r, you get 0.5 of the efficiency. Okay, so a 10 kilogram projectile is launched from ground level and angle 6 degrees above the horizontal with an initial speed of 12 meters per second. Okay, so this is what it looks like initially. 10 kg, it's traveling at 12 meters per second, 60 degrees above the horizontal. The point of flight when its vertical component of its velocity is 0 and it's reached its max height. Let's call it h. So yeah, it's going to be traveling with that direction. It splits into 2 pieces P and Q, each of mass 5 kilograms. Immediately after projectile splits P So let's draw P in red. 14 meters per second to the right, and it is 5 kilograms. Okay, so to conserve velocity, because there's no initial vertical component momentum, Q also has to be traveling horizontally at this point. So this is Q. So it's also 5 kilograms. And it's traveling, let's say, at this point it's traveling with speed UQ. What is the speed of piece Q immediately before it hits the ground? Okay. So what we need to find is, okay, so afterwards we need to find UQ, but to do that we need to find this speed up here. Let's call that, okay, so that speed up there is going to be, that's easy because the horizontal component of the speed doesn't change, so U is going to be 12 cosine 60 degrees, which is 12 over 2, 6 meters per second. So now we can conserve momentum in the horizontal direction to find Q. So from here to this situation, we can conserve momentum. So we get 10 times 6 equals 5 times 14 plus 5 UQ. That means UQ equals 2 times 6 minus 14, which is minus 2 meters per second. So Q is actually going to be moving this way at 2 meters per second. Okay, and then it falls through a height h. So we need to know what that height h is. So let's think about the vertical component of motion of the projectile as it goes from here to there. We'll think about this vertical component of the motion. So distance it travels upwards. So we're gonna, the distance it travels upwards is h. So it will result for upwards. The initial component of that speed is 12 sine 60 degrees, which is going to be 6 root 3. Yeah, because sine 60 is root 3 over 2. The final vertical component of the speed is 0. The acceleration is minus g. So v squared minus u squared equals 2as. That means h equals v squared, which is 0, minus u squared, which is 36 times 3 over 2as, 2 times minus g, which is going to be minus 54 over g. That's going to be the height it travels through. No, sorry. 54 over g, the minus is cancelled. The negative, yeah, the minus 1 cancels. Okay, now let's think about q as it falls. So resolve downwards for q. So it falls through a height h. Initially it's got no vertical speed. It ends up with vertical component, let's call that Vy. Which we're trying to find. And then it's got acceleration g downwards. Okay, so v squared minus u squared equals 2as again. That means vy squared minus 0 equals 2gh, which is 108. So that means vy squared equals 108. So vy is going to be root 108. So when q hits the ground, it's got 2 meters per second that way because the horizontal component doesn't change, and then vy that way. So the total the speed of q is going to be v, which equals root vy squared plus 2 squared, which is going to be root 108 plus 4, which is root 112. So let's factorize 112, that's 2 and 56, that's 2 and 28, that's 2 and 14, that's 2 and 7. So v is going to be 4 root 7. There we go. That's find the density rho of a sphere varies from its center to its surface according to the equation this, where x is the distance from its center, r is its radius, and rho is the density at its center. What is the mass of the sphere? Okay. So basically, the way we're going to solve this is by using calculus. Yeah, we're going to have to. So the way we're going to do this is we think about this sphere as like kind of like an onion, like made up of many smaller spheres stacked up inside, each with width dx. And as dx gets closer to 0, the approximations we'll be making to figure out the mass of each of these is going to get better and better. So as dx gets closer to 0, what we're going to have is that the density throughout one of these rings is going to become like more constant, so it's not going to vary as much. So we're going to push dx get in the limit. Yeah, we're going to make dx get closer and closer to 0, so the density throughout them is constant. And so let's figure out what the mass of one of these rings is going to be. A generic one, a distance x from the center. So we can basically say, because as dx gets closer and closer to 0, we can pretty much say that it's going to be the surface area, because the inside, this inside surface area and the outside surface area won't vary too much. So we can basically say, because their radiuses only differ by the distance dx, which shrinks rapidly, which goes to 0. So we can say that the volume, so dm equals rho dv. So we can say that the volume dv is going to be the area of this, the surface area, times dx. And the surface area of a sphere is 4 times pi times its radius squared, right? So that's x squared. So dm equals rho dv, which is a dx, which is times 4 pi x squared times dx, which is going to be 4 rho pi x squared dx. So yeah, so dm is going to be 4 rho naught times by 4 rho naught pi times by x squared minus x cubed over 2r dx. So the mass of this sphere is going to be, if we integrate dm from x equals 0, so we add up the smallest sphere at the very center to the smallest spherical shell at the very center to the largest spherical shell along the outside. So that's x equals r. So then we get this basically 4 rho naught pi so m is going to be 4 rho naught pi, increase the power by 1 divided by the new power, increase the power by 1 divided by the new power, that's r and 0. 4 rho naught pi times by r cubed over 3 minus r cubed over 8 minus 0. So that's going to be 4 rho naught pi times by 5r cubed over 25, sorry. Yeah, no, 24. Which is going to be 5/6 rho naught pi r cubed. Is that an option? Yes. B.
Thank you for watching, everyone. Hope you found it useful. And for more ESAT practice and preparation resources, make sure to check out our website. Link will be in the description.